Wow, what's going on here? Drawing tangents and normals to curves with calculus? Why would we do that? First of all, what's a normal? Do you know? We'll have a look at that in a minute. Here's the burning question. Why would you want to draw tangents? Here's one up here. Draw a tangent to the curve y equals root x. We know that the instantaneous rate of change at this point is the value of the derivative dy by dx, or f dash x. But do we actually want to find the equation of the tangent and draw it in? And over here are both of them. The tangent is the line which just touches at a point, and the normal is the perpendicular at that point, perpendicular to the curve or to the tangent at 90 degrees. Okay, 90 degrees to it. So, okay, that sounds like a good mathematical exercise. And we have spoken about instantaneous rate of change being the slope of the tangent at that point. But why would you actually find the equation? Well, I'm going to give you just a little moment now, a few seconds now, to look at this drawing down here, or this graph, this diagram really, and see if you can work out the connection between this diagram and therefore some reason for finding the equations of tangents and normals. Okay, look at the green arrows and look at the red arrows. Okay, have you got any idea? Okay, well, let's have a look. This is a body or point P travelling in a circular path. Okay, so this is a bit of applied mathematics now, applying it outside just the mathematics realm to rotational motion in physics, for example, rotational motion problems in physics. Okay, so it's got a circular path. I don't know whether you know much physics, but to keep a body or a point P moving in a circular path, here it is here, you have to have an inwards force. It's called a centripetal force. Centripetal force. Okay. So that the point P is held in that circular motion. Now, we're not going to do much of that. But that centripetal force is acting at right angles to the linear motion of the point P. Okay, and if you release that force, this would be the final path. This would be the tangential velocity would follow this path here, tangential velocity. It's the path that the body would follow once you release the force. So can you now see some value in finding the actual equations, not just the slope, but the equation of the tangent? Because that would give you a good description of where that body's going to head when you release that force. And the equation of the normal is going to give you a good description, if you had a grid system, of where the force is acting, the direction, and everything about it that you would like to know there. Okay, so we've got that link. We're not actually in this course going to be doing any of this sort of application as such. Okay, we're just going to go into the formal process of getting equations of tangents and normals. But keep this in mind, because this is useful later on. It's in the background of everything that we're doing. So when you are doing some work then, you're finding it fairly tough, think, well, this is useful, okay, in a further application of applied mathematics. Let's go on and have a look at finding the equations now. Oh, now this is revision. I'm going to put it up here. This is revision. I hope it's revision. It should go back to grade 8 and 9 and 10 maybe. Revision. We want the equation of a straight line. The equation of a straight line. And I've got one over on the left there on a grid. So let's see if we can work with that. I think most people are taught equation of a straight line is given in the form y equals mx plus c. And that's okay too. Let's look at the theory of that. That says, well, if you think over here at starting with the intercept on the y-axis, which we're lucky enough to have here, 0, 3. then you can think of the line, so they're starting there, you can think of the line as having a constant slope or gradient of m. That means what? The delta y on delta x is m over 1. So every time you move 1, come back over here, in the x-axis you move m, right? It's a constant slope. Every time you use 1 you move m. So that's why the equation would be thought of as, to get the y's of points, you start off with c, that's the first y, and then the next y is x lots of m further on. So if you change x to 3, you'll have 3 lots of m and so on. Okay, so this is the idea here. X lots of m gives you the necessary movement along the line. That's why mx plus c works. Okay, we don't put x lots of m, we use this. But the notion of it is to start, come over here again, is to start at the point C, and then for every x you're going to move up m, so it's going to be mx plus c. Do you get it? Now, what you need to do if you're going to use this formula, which is not the preferred one, you would probably only use this like in this problem here, where you've got the intercept. So you put y equals mx plus 3, you know it. Then you substitute in the slope, which would be, what would it be? dy by dx, wouldn't it? For the straight line. Or f dashed x, or y dashed. That's what the value of the derivative gives you, the slope of the tangent at the point. So now we're just going to put those values that we've been finding in this equation. Let's do it. We don't usually use this one, but let's do it for the equation on the left here. Let's imagine we didn't know the y-intercept there. Let's scrub all this out. You could take a point on the line. Let's take 3, 9, and another point is 1, 5. Okay, in the usual way of using this, we would say the slope is, well, let's do it over here, delta y on delta x, change in y, 9 take 5, change in x, so it's 4 over 2, or 2. That's doing it without calculus. So y equals 2x plus c. If we didn't know this, we could sub in a point. Let's sub in 1, 5. Doesn't matter which point you sub in, it will work because they're all on the same straight line there. So you've got 2 times 1 plus c, subbing in 5. Forgot to sub that in, 5. So 5 equals 2 plus c, 3 equals c. I've constructed my equation. Fairly long way there. That's assuming you didn't know the y-intercept there. So that's the mx plus c method, isn't it? Where you construct, you get the slope, you don't know c, you sub in the point, find c, reconstitute the equation. Now, many of you might be actually using that method for more sophisticated problems and applications later on. It's probably not the best method. Okay, so let's have a look at another method now. You can always rewind this and have a look back at what I've done there. So let's have a look at the other method. Now the other method starts the same way with the calculation of the slope, which we're going to replace with dy by dx, a value added at the point, or f dashed x, whatever you want to call it, y dashed. But let's look at the theory of this one now. It behaves differently now. What we're going to say is, if we wanted the rule, and remember the equation is a rule, isn't it? It's a rule over here. It's a rule that points must obey to form that straight line, to be completely lined up. So this is one way of thinking about it, the constant step up, the constant slope starting at the y-intercept. The other one, come over here now, is to say, well, if I had a general point further out the line like that, no matter where it was, the slope, the y delta y step over x step, must be the same between my general point, any point I'm trying to get a rule for, and either of these points. So I could say, well, let's do delta y and delta x between these two. So this would be y take 9 over x take 3. Coming up here, working out the delta y, that's y take 9, and the difference in the x take 3. And that always has to come to the slope, which here worked out in the same way with the derivative, is 2. I'm just doing revision of our year 9 and 10 work here. And you could use this point, because obviously it doesn't matter which 2 points you use on the line, the slope is the same. It's got a constant slope. Okay, what do you do here? Multiply both sides by x take 3. So y take 9 equals 2 times x take 3. Y equals 2x take 6, add 9, so y equals 2x plus 3. Same answer, of course. Now this method is much better if you have nasty fractions for points and things like that, or pronumerals if you're working with an unknown point of contact, which we will be later on. This is a preferred method. So you might use this, I think is preferable. Use y equals mx plus c if you actually know the y-intercept, which generally we won't. Okay, so choose your method. Basically, in this presentation we'll be using examples from Pearson's, and I'm going to go through all the Pearson's exercises, examples and exercises. Then I'm going to add some from Hayes and Harris, which look a little bit different. So go the whole way. That'd be good for you to have copies of those books, e-copies or hard copies, handy by there. You won't actually need them. You'll be able to see it from the presentation, but you could back it up there. All right, let's go and have a look at some of those examples then. So here's the first one from Pearson. So let's just bring it up here. Find the equation of the line tangent to y equals root x. That was on the first window of the presentation. Use this tangent line to approximate root 10. Oh, don't know what they're talking about with that. Let's find the equation of the tangent for a start. So here it is. I've just said what I've said up there. We can find the equation of any line if we know its slope and the point it passes through. Okay. Now, so at x equals 9, you can say by subbing 9 into root x, the y value is 3. So we've got a point on the line, 9, 3. Now we're going to get the derivative. We've only got 1 point on the line. So now we're going to use dy by dx, which is differentiating root x. Root x is x to the half. The x to the n rule, half x to the neg a half. So it's, if you like, it's a half, there's the half. And x to the neg a half is 1 on root x. Easier to evaluate in that form. So now we've got to find the slope. X is 9, so we put 9 in here. 1 on 2 root 9 or 6. So we now have the slope. So all that we're doing differently in this presentation is the way in which we find the slope. Method of obtaining the slope is the only new bit. And that's not really new to straight line work, but it's the calculus stuff, of course, where the slope of the tangent is the value of the derivative at that point. Okay, now they sub in. Now they've done it slightly differently here. I would be saying y take 3 over x take 9 equals a 6. I'm using the form y take a known y over x take a known x is m, if you like. Okay, they've multiplied it across already. Okay, so multiplying this across here, we get this, and then simplifying it. Okay, Alright, so choose your method. You can use mx plus c, but this is probably going to be more useful for harder problems. Let's go down and look at what we've done. We've said here, this was from the first window of this presentation, at that point 9,3, the equation of the tangent is this thing here. Okay, so you get a picture there, and you could draw that on with the calculator. I'm going to later on show you how the graphics display calculator will calculate and draw this for you. Okay, but just remember, in paper 1, we're not using calculators, so we've got to be able to do it by hand. Okay, so there's an important point here now. See this tangent, okay, at the point when x is 9, we know the root of 9 is 3. And also putting it in here, putting 9 in there, you'd get 3. But gee, it's not far out even up to here, is it? There's not much gap between the tangent and the curve. So even at a value like 12, it should be 12 and root 12, but we don't know. But we could say, oh, well, approximately, this will do, because it's not much off tangency, so we could stick 12 in here and have an approximate root for it. Okay, so over here is Pearson's statements. For values of x near 9, we're going to say this is close enough to tangency, even at points not actually at x equals 9. So it's approximation. So could you go up to 10? Yep. 10 over 6 plus 3 over 2 is 19 over 6. And that's pretty close. What's it about? Let's clean all this off here. What's it about? It's about this gap, isn't it? Okay. When, and we talked about this before, that gap means you're averaging the effect. It's not tangent there. It's not a tangent there or down here. So approximately, what would you say? Somewhere between 5 and maybe 13. Somewhere there before the gap opens up. We could use this as an approximate tangent across that range of x values probably, and get an approximate point of contact, which would be the root of the number. The value y there would be the root of the number. Now, it's not a bad little trick, is it? That's just a little oddity along the way. Bit of fancy math there. Okay, let's go down and look at another example. Example 20 here. Find the equation of tangent to this function at this point. So they're telling you that a half 5 on 2 lies on the graph of the function. Okay, let's try and get the derivative. So the function has to be simplified to x plus x to the neg 1. So we've got an x to the n rule. Okay, derivative of x is 1. Derivative of this, x to the n rule, neg x to the neg 2. Which is 1 take a negative power is 1 on x squared. So subbing in a half, we get the value neg 3. Just watch this. In paper 1, you won't have a calculator to do it, so it's 1 over a half squared. Let's just unpack that. That's 1 over a quarter, which is 1 times 4 over 1, which is 4. And it's 1 take 4 is neg 3. So just make sure you can do work with fractions, particularly division, where you invert and multiply. I wonder if you know why you invert and multiply. Think about that one. So the slope of the tangent is neg 3. Therefore, we're going to say y take 5 over 2 over x take a half is neg 3, and then multiply across. And they've gone to that step there. And then we have to simplify all of that. Here it is here. Working with fractions. 3 halves plus 5 halves is 8 halves, which is 4. Think about it like that. So there we have the equation. Alright. So that's a pretty straight one, and that's the skill we want to build up fairly quickly. Let's have a look at another example here from Pearson's. Example 21. Here's a function x squared x take 1. Find the 2 points on the graph of g at which the slope is 8. Oh, this is going backwards. We know the slope now. Okay, so the slope in this work, we're going to use the derivative, aren't we? So we know the value of the derivative. See that? Working backwards there. So here's our function down here. let's expand it so we can use the x to the n rule. Then getting the derivative of that, it's 3x squared take 2x. X to the n rule on both these powers. Okay, so there, what that means is then, is our derivative has to equal 8. So there we have a quadratic, and we can factorise it, or you can use the expression for the roots of a quadratic. This is in the information booklet, a formula booklet that the IB give you. So here we have -4/3, or x is 2. So we want to find the 2 points, so they are the x values. To get the y values, sub -4/3 back up in here into the function, and there it is, -4 thirds cubed take -4 thirds squared, and the same with the 2. So the 2 points are this, -4 thirds, -112/27 and 2, 4. Don't forget, you must have the y coordinates if they say find the points. A lot of students just say, oh, I've got the x values. That's okay, but they said find the 2 points. Let's see, y values as well. And now we're supposed to find the equations. So let's come down and do some equations. First of all, at this point, what are we going to do? Y take -112 on 27 over x take -4 thirds equals 8. And then multiplying across. They've gone multiplying across. Messy fractions here. Okay. Change it all to 27ths without a calculator. This would be 9 times 32. Okay, have to do that. 9 times 32, 288 minus 112 is 176. So just multiplying here by 9 and the top line by 9 to get 27ths. That's in case you get caught in paper 1 with this sort of work. Pretty unwieldy looking tangent. There it is there, tangent at 2, 4, y take 4 over x take 2 is again 8. They were parallel. Then multiplying across, you have this, and there we have our tangent. And if you drew them, here it is here. They both had slope of 8, that was correct, so they're parallel, and one was at -4 thirds over there, and the other one was at 2, and they are parallel. Very nice. Okay, now that doesn't really look like a very steep slope of 8, and the reason for that is the different scales on the x and y axes. The y-axis scale is going up 2 for every unit, and this one is only going up 0.5, so there's a scale difference. So just watch that when you're drawing tangents. You might say, gee, this is a steep slope, that doesn't look right, and it's because of the different scales here on the axes. How are you going? Not too bad, this one, is it? Okay, well, let's keep going. What about this work here now? This is a normal at the point P. There it is, it's at 90 degrees to the tangent or to the curve. The slope of the curve at the instant is the slope of the tangent. I can't help myself, I've got to do it. Halley's trichotomy here, the derivative, remember now, the derivative, when we say that, we're thinking about the slope of the tangent, or we can think of the instantaneous rate of change of the function. Okay, so the instantaneous rate of change is, if you like, the slope of the curve itself at that point, the slope of the tangent. They're all the same. Please think about this as we go round and round. So now what we're interested in is this normal up here. And here we have Pearson's definition. A normal to a graph of function at a point is a line through the point that is at a right angle. Not a bad idea when you're reading maths to underline key words. Okay, so at that point, the normal and the tangent are perpendicular. Okay, there it is in there. That's what we're talking about. Let's give them the word normal. Okay, let's go down and see if we can calculate some of those then. Here we are. And to do that, we have to recall this. Two perpendicular lines have slopes that are opposite. Oh, don't like opposite. Negative reciprocals, I like. negative, not opposite. Negative reciprocals. If the slopes of two perpendicular lines are M1 and M2, then their product is neg1. I see that as a fundamental definition, or using it, one is mine as a reciprocal of the other. So let's take an idea here. M is 3/4, let's say that's one of them. Then the other one has to be neg4/3. Okay, and generally you put the negative probably in the top line there. Just remembering here, these are all the same, aren't they? These are all the same. There's a bit of revision here. Okay, it doesn't matter where you put the negative. You can't put negative top and bottom because a negative divided by a negative is a positive, and you want an overall negative answer. There it is in there. So I'd put neg4/3. You can put these two. You want to know why I'd put neg4/3? Because usually in maths we consider a positive move in the x direction, and we look at what is the resultant in the y. Okay, so this one doesn't cut it, because that's suggesting we move neg3 in the x for a 4 in the y. So that's anti-conventional, that's unconventional. We usually would talk about a positive move in the x direction, there it is, and what is the y response? Neg4. Okay, so I like neg4/3 rather than either of these two, for that very, very important mathematical reason. Just keep down here, you keep an idea down here. The exception is one of the lines is horizontal, the other is vertical. So a horizontal line, let's just quickly whip one in here. Horizontal line, here we go, through here. Let's make this our line. So M is 0, so, and the equation would be something like y equals a constant, y equals 5 or something. So the perpendicular line here, that's M1, M2 would have slope undefined, and its equation would be something like x equals 2 or something like that. X equals constant. Bit of revision of the old coordinate geometry there. Alright, let's go down and have a look. Example 22 here. Find the equation of the normal. So we're going to find the normal at a point. Okay, so they've given us a point, so we don't have much work to do. Let's find the derivative first, which is 4x take 6. Same thing when x is 1, it is neg2, 4x take 6. Hence the slope of the normal is, we've reversed it here. Alright, m2 is minor is reciprocal of m1. And therefore the equation will be, let's take the point, y take neg1 over x take 1 is a half. And then multiplying it across, you multiply it across, or cross multiply, 2 by y plus 1 equals 1 by x take 1. Okay, you might like to do that instead of multiplying by a half, because it gives you 2y plus 2 equals x take 1, and you can use this form now. Put that across, 3 equals x take 2y. So it can be used in that way to get the general form of the equation of a straight line. What have we just done? Well, let's have a look at this diagram here now. Our normal is a half x take 3/2. Our tangent would have been y equals neg 2x plus 1. We weren't actually asked to find that one. Okay, how are you going with all this revision of straight line stuff? Hope it's not too hard. Okay, let's have a look at example 23. Consider the parabola with the equation y equals a quarter x squared. Oh, find the normals. What's that? Normals, not tangents, at neg 2, 1 and neg 4, 4. So they're being kind to us. They're not making us find the points by just saying x equals neg 2 and y equals neg 4. They're giving us the y coordinates as well. Show that, here's a variation. Show that the point of intersection of these two normals lies on the parabola. First step, as usual, find the derivative. For the first point, find the value of the derivative, so put in x is neg 2, half neg 2 is neg 1. So the slope of the normal, don't forget, minus the reciprocal for a perpendicular line, and then therefore we can find that equation. Y take the y point of a point on the curve, a y value, x take -2 is 1, and then they're multiplying across here there. So oops, hang on, I think I put in the wrong one. Oh no, that's alright, that's the point -2 1, -2 1, yep, that's good. Okay, alright, so slope of the tangent at the other point, so put in x is -4 into the derivative, get -2, don't forget it's a normal, so the slope is minus 1 over -2, or just a half now, so it's y take 4 over x take -4 equals a half, and probably I would go that way, 2 by y take 4 equals 1 by x plus 4, and so on. 2y take 8 equals x plus 4, or -12 equals x take 2y, if you wanted it in the general form. If you do it this way, just multiply across, leaving the half there, you'll always get it in slope-intercept form, y equals mx plus c form. Let's have a look at showing the points of intersection here. Find the points of intersection. So here is the first one. There's our first equation and our second one, because at their point of intersection, of course, there is one common point and the y's will be the same. So the y's are equal at the point of intersection. So that's how we're going to find the point of intersection. So a half x, subtracting a half x from both sides, get a half x, subtracting 3 from both sides, get 3, so x is 6. Then how would you find the y? You can actually sub it into either of these equations and you get 9. So the intersection point is 6, 9. Okay, so and then just checking here that it works, subbing 6 into the original parabola, you get equation of the parabola, you get that. So it's just checking, so it's confirming that the point that you've made up, you haven't made an arithmetic slip here somewhere, it is on the curve. Alright, so you can see there's some variations that they could make you do, but if you know your basic stuff, then that's good. Just noticing here, it was better to leave it in this form and not cross multiply there, because it enabled us to put the two y's equal. Y equals x plus 3, y equals half x plus 6. Now, you might be wondering, can the graphics display calculator do anything for me in this work? If we're in paper 2 land, yes you can. Let's have a look at the Casio. Pearson's using the TI, but here's the Casio. Lots of little calculators sitting there. So first thing is you go to graph mode, and so click on that and enter graph mode. Before you do anything else, I want you to, here we are, shift and menu in here to set up, and up comes this window, and you should be in math mode, but this is what we really want down here, derivative on. So scroll down and make sure the derivative is on, because the calculator now is going to not only calculate the slope of the tangent, it's going to draw it and give you its equation as well. Oh, that's good. So enter your function, a quarter x squared. I'm doing a little bit from that last problem up there, and draw that, hitting execute. I have to check your view window. I've used initial view window here, just remembering view window is shift in here and then F3 to get that view window there. Okay, so when you have got this graph, what we now want to do, I'll just grab this out, is to hit shift again, and this time we want sketch. See it there? So shift F4, sketch, and we get these options. So what we're going to do, I'm going to draw the tangent, so there it is there. So I'm going to hit F2, and up comes this window over here now. Come back over here, it come up, it'll always start with x is naught, y is naught, and showing you the value of the derivative. So what we want though, we want the point, let's say -2. So at this stage we just hit -2 and all of this comes up. You don't have to wait for the prompt. Just enter the x value at this window here. -2, up this comes, and if you hit execute we get this window and it's saying I'm going to look at the point -2, 1, and there's the value of the derivative. If you now push execute, what comes up is beautiful. Look at this. There's the equation, the whole equation of the tangent at -2. No work. Oh, but they may put this in paper 1, so that's the problem. You've got to be able to do what we were doing up above. But there it is. And if you went again and did shift and F4 to get sketch and then hit normal, it will draw the normal for you. There it is there, and there's the tangent still on there as well. So you can actually keep doing it and it will display the equations and show the graph as well. So pretty powerful stuff. There, Pearson's uses the TI, so have a look at some of their solutions. But when you have a look at the solutions, you can get your calculator out if you're using Casio and do it on there as well. Alright, let's go down and have a look at some problems. So here are Pearson's problems. Don't forget, when we've done these, we're going to come back and do a couple of variations from Hayes, and Harris. So, usual process, I want you to pause the presentation and have a go as we go through, and then scroll forward, check your answers as you go through. Okay, there's question 1 to 5. I think there's only about 10 or 12 of these. Have a look at question 6. Yeah, question 6 through 10 there. Some just good warm-up questions there, some little thinking questions there. Okay, let's have a look at the solutions now of those 10. That's question 1, A, B and C. I would prefer you work down the page rather than across. Often people would do this in textbooks to save space, but mathematically you should be working down with sequential steps under each other. Okay, that's 1A, B and C. Let's look at D now. There's D. And then we'll have a look at question 2. Let's see if we can get all of question 2 up there. We get most of it. Okay. And there's the rest of question 2. Go to question 3 and question 4. Okay, let's go to 5. 5 and some calculator work down the bottom there. The rest of that, showing the tangents. Let's have a look at question 6. Question 7 now. Oops, we'll just go back up a bit there. Question 7, part of 8. 8's a bit more theoretical. And there's the rest of 8. I'll bring up 9 and 10 in a minute. There's 9, and we'll just finish off with 10. And there's 10. Okay, how are you going there? Right, we're going to move on with some other variations with Hayes, and Harris, and finish with the practice questions from Pearson's for the whole chapter 11. Okay, so here's an example of a variation. find the equations of any horizontal tangents. Okay, so obviously we have a function. Slope of the tangent is the value of the derivative. 3x squared, take 12 here. Remembering the derivative of a constant is 0. So we want to know when these are horizontal. So that equals 0. Factorising out the 3, then factorising x squared, take 4, x plus 2 by x, take 2. There are two values at which the slope of the tangent would be 0. Remembering, you can also put this equal to 0. As long as you remember with a quadratic, there are two solutions. X squared equals 4, x equals plus or minus 2. Okay, and you could draw them. This is Casio, not the 9860 plus, different model Casio, but you can draw those tangents as I've indicated up there. So let's have a look. Let's find the equations. When x is 2, what is y? So we're going to have to put that back in here. X is 2 to get neg 14. When x is neg 2, put it back in the function to get 18. So we've got the two points there. And of course, because they're horizontal implies the slope is 0. It also implies the equation is y equals a constant. So you don't have to go through mx plus c or y take ya or whatever. So it'll just be y equals neg 14, y equals 18. Please notice that. Horizontal line means slope is 0, but here's the basic equation. Here they are up here, they're flat lines, so y equals a constant. Just go straight to it. Pinch the y value from the y point, the y coordinate of the point on there. So that's an easy one in that sense. Alright, let's do a couple. Okay, here's some from Hayes and Harris. A couple of questions here. A few variations. Watching out for this sort of thing. You've got two unknowns. You're going to need two equations. Right? One involving the derivative and one involving the function, then solve them simultaneously. That sort of thing. So watch that. I've got these in as curly ones to keep you thinking. Let's look at the solution. So pause it, have a go, and then look ahead at the solution. Here we are. Question 3. A and B. I think that's almost all of C there. And D. Let's have a look at question 4. A and almost all of B. And there's B. Okay, interesting little variations. Now I've got one more for you, and then we'll go into the practice questions. Here we go again from Hayes and Harris. Find the coordinates of the points where the tangent to that at 1, 4 meets the curve again. Now that's different. Let's go through the same process. We have a function, we have a derivative, and we know it's at the point 1, 4, so subbing in 1, we know the slope is 4. So let's work out the equation. Y take 4 over x take 1 equals 4. Multiplying across, we've got a nice easy equation for a tangent y equals 4x. Where does it meet it again? So it'll meet it again when the function equals 4x. That gives you this one here. Now, if there's a point of tangency, there's a repeated 0. So here, there will be x take 1 squared, because it's a tangent at x equals 1. That's not strictly speaking in this course, because we don't do any polynomial stuff in this course, but that's an idea. And if you expand this, the highest power would be x squared. So this term would be x. And if you expanded this, the answer would be 1, and you need a 2 down the end. So here that would be a 2. So you're sort of working it out by what? Backwards from expansions. Backwards from expansion. Working out that that number is a 2. So it's going to be at x equals -2. Let's go down a bit. So x equals 1 is where it's tangent, and x is -2 is the other one. X plus 2 is 0, so x equals -2, and then working out the y value of the point by subbing -2 back in the function, and therefore getting -8 here. So there it is, it's touching there at 1, 4, and cutting again at -2, -8. And you could actually do that, so there, then state the answer clearly. You actually do that on the calculator. But remember, in paper 1 you are expected to be able to work things out without a calculator. Let's have a look at question 10. One like that. Find where the tangent meets the curve again, so practice some of that. Let's look at the solutions now and have a look. Question 10, A and B, almost all of B. Let's have a look at B, the rest of B. Same stuff, get into a pattern there of what's going on. Let's look at C. There's C. A bit nasty fractions there. Look at D. And I do make a mistake. There's one more example I want to show you from Hayes, and Harris. Find the equation of the tangents to y equals x squared. Oh, from a point, danger, danger, because we know, here it is, a point, but we don't know the point of contact, so we don't know the slope of the tangent because we don't know where on the curve it's touching. Okay, so we can't just sub the x value into the derivative, get the slope. So we've got to do this. Let a squared lie on that. So in other words, you let the point of contact be x is equal to a, and then you sub a into the function. That's the method. Okay, so then we can work with it. Derivative is 2x, so the slope of the tangent is 2a. So at our fictitious point here, the slope is 2a, so we can now say y take a squared over x take a equals 2, and go on with that idea here. So what have we got? I think, y take a squared, x take a, that's good. Do we get the same thing here? 2x take 2a, what have we got here? X take a, I'm getting something slightly different there, aren't I? Y take a squared over x take 2, oops, left out an a. Slope is 2a, not 2. And then when we multiply across, we get what Hayes and Harris have got there. I left out 2a, so there's the slope of the tangent. Okay, so we agree with this thing, but now to find a, we use this trick. We know it passes through 2, 3, therefore x equals 2, y equals 3, satisfies that equation, and so we can sub those values in there. X is 2 and 3, and we can backtrack and find a. So a is 1 or 3. So at a is 1, the equation of tangent would be this, sticking it back in the equation of the tangent line up here, and the point of contact would be 1, 1, or at a is 3, sticking that back, you get this point of contact 3, 9. So there's actually 2 tangents there. And can we see it from the graph? I think we probably can. Let's grub this out here. Now, what's drawn here is 1, isn't it? This is about 1, because this is 2 there. So this one is the point 1, 1. And then if we continued this, there would be another tangent up here. Can you see that? We could draw, not the same tangent. If I'm trying to draw it in here. So there's another tangent there. This would be the point 39. That's the idea. From 2, 3, you can actually draw tangents to y equals x squared at two different posies. Here they are here. So please remember the little method here. Because you don't know where the tangent's hitting the curve, you've got to let the point A, f of A, this is better, A, f of A, be the contact. So you let the point have x value A and then you sub it into the function value. So you create a general point of contact. Okay, are you ready? See if you can do that now in question 11 here. Okay, so here it's telling you let the point be of contact bx equals A, so it gives you a starting point. Okay, some interesting little twisty bits there just for some of the possible harder questions. Being a new course, we're not sure the structure of those questions yet. Okay, let's go and have a look at the solutions to that one. Oops, just go back up a bit. Okay, so there's question 11A. Fair bit of work, fair bit of algebra in this because we don't know that contact point, so we're getting A's and things in the derivative as well. Okay, see what you think about that. Let's have a look at part B. We'll see if we can get C on there as well. There's B. Have a look at C. There's the rest of C. Nasty A expressions here, 1 on 2 root A. Alright, now the last thing I want to do here with you is to go back to Pearson's practice questions for chapter 11. So let's have a look at them. I think there are 15 of them. So here are the first 3, and down below I've got the fully worked solutions for you. So question 1 to 3. Pause it and have a go. And let's go to question 4, 5 and 6, or 4 through 7. 8 continues on, so we'll have a look at that in a minute. 4 through 7. Question 8, there we are. Interesting one, bit confusing. To think about that one. 9 and 10. When we get 9, there's 9, 10. We need a bit more room. Okay, so we might have to scroll up and down for 10. Because there's a table. Okay, so we'll just go there. Have to scroll back to look at the graphs. Copy and match each function with its derivative. Copy the table. Okay, this is from 2002 they asked this question. Okay, so you have to scroll back and have a look at those to do the table. 11 through 13, I think there's a bit more of 14 and 15 to come. Okay, there's 14 and 15. Okay, going to our motion problems or kinematics from before. Okay, let's have a look at the solutions now. Okay, 1A, B and C. Have a look at D now. D through H. Let's look at question 2. 2 and 3. Go to question 4. A and B. 5, 6 and 7. 8 and 9. Is that derivative question, question 10. 10 and 11. 12. 13. 14 and 15. Wow, are you happy with the way it's coming along for you there, the sorts of things that we're building up to? I hope you are. There's a little bit more of calculus to come. You might be thinking now, we're working with fairly basic functions. Are there any functions you'd like to find the derivative for? And the answer to that is going to be in the next presentation. See you then. Cheers for now.